Hello, I am Isabella Ziccardi from Bocconi University and I am one of Luca's postdoc. So today I want to talk about hypergraph sparsification and generic chaining. I never did research about this topic, but I wanted to talk about it because I started to study the subject 1.5 years ago, just right after I moved to Milan for joining Luca's group. So I studied this subject upon suggestion of Luca, and also Luca worked on it 5 years ago, and he has also a series of blog posts about it. So I start with the concept of graph sparsification. We have a graph G, and the main goal is to find a graph G prime which is a subgraph of G with the same set of vertices but with less edges. We want also that G prime is close to G respect to some metric. We know that any graph G can be represented by its adjacency or Laplacian matrix. The adjacency matrix A of the graph is defined such that the element uv of the matrix is equal to the weight of the edge E if E is present in the graph and 0 otherwise. The Laplacian matrix is the diagonal matrix of the degree minus the adjacency matrix. For any graph, we can take a subset of vertices S and define the cut of the set S. So we consider all the edges in blue that have one endpoint in S and one endpoint outside S, and the cut of the set is the sum of the weight of such blue edges. So we say that a graph G prime is a cut sparsifier of the graph G with error epsilon if every cut in G is approximated by a cut in G prime with error at most epsilon. So Benzur and Karger gives a construction of a cut sparsifier with error epsilon with epsilon minus 2 and log n edges with high probability. We can also have a stronger notion of sparsifier with the spectral sparsifier. So we say that the graph G prime is a spectral sparsifier of G with error epsilon if the quadratic form of the Laplacian of G for every x is approximated by the quadratic form of the Laplacian of G prime with error at most epsilon. If we restrict x to be a 0-1 string of n elements, this definition is equivalent to the definition of a cut sparsifier. So every spectral sparsifier with error epsilon will be also a cut sparsifier with error epsilon. Spielman and Srivastava show a construction of a spectral sparsifier with error epsilon with epsilon minus 2 and log n edges with high probability. They do it in the following way. They define a graph G prime by sampling epsilon minus 2 and log n edges of G, where each edge is sampled independently with probability PE, and each selected edge is weighted with weight WE over PE. They choose the value of the probability PE to be proportional to the effective resistances of the edges E. Then they study the concentration of some matrix norm that depends on the random matrix LG prime, where G prime is this new graph. Okay, so the effective resistance can be seen as a function of the Laplacian of the graph, but they also can be seen as the probability that a random walk starting at U visit V for the first time using the edge UV. So this is the effective resistance of the edge UV. For example, in this picture, we can see that the effective resistance of the edge UV is equal to 1, because the only way to go from U to V is using the edge UV. Alternatively, the effective resistance can be seen as the probability of the edge to be included in the random uniform spanning tree. Now we will talk about hypergraph sparsification. So we have an hypergraph H, which is defined by a set of n vertices and a set of hyperedges. where the hyperedge generalizes the concept of edge, and it's not a pair of nodes but more generally a subset of nodes. Each hyperedge has some weight WE, and we define D to be the maximum cardinality between all the hyperedges. Also in the hypergraph we can define what is a cut. So fixing a subset of vertices S, we consider all the hyperedges that has as a vertex in S and a vertex in the complementary of S, and the cut of S is the sum of weights of such hyperedges. So as in the graph case, we can define the cut hypergraph sparsifier, and we say that the hypergraph H prime is a cut sparsifier of H with error epsilon if every cut in H is approximated by the cut in H prime with error at most epsilon. And Chen, Kan and Agda show a construction of a cut sparsifier with error epsilon with epsilon minus 2 and log n hyperedges with high probability. To introduce the notion of spectral hypergraph sparsifier, we need to introduce the hypergraph Laplacian quadratic form. So this is defined to be for each vector x as the sum of all the hyperedges of the weight of the single hyperedge times the maximum between all the nodes in the hyperedge of xu minus xv square. I recall that the quadratic form of the Laplacian for the graph was this quantity, so here they introduce the maximum. So we can define the spectral hypergraph sparsifier. We say that the hypergraph H prime is a spectral sparsifier of H with error epsilon if the quadratic form of H is approximated by the quadratic form of H prime for every x with error at most epsilon. So also in this case, if we restrict x to be a 0-1 string of n elements, this definition is equivalent to the definition of the cut hypergraph sparsifier. So as in the graph case, we can define the sparsifier H prime of H by sampling hyperedges independently with probabilities P and weighted with weight WE over P. So in the graph sparsification, we do the same thing, and then we have to prove that the quadratic form of G prime is approximated by the quadratic form of G. So we have to prove this inequality for every x in Rn. So if we apply the change of variables given by this formula, we obtain that this is equivalent to asking this inequality here. That holds for every y that is orthogonal to the vector with all 1. So this is equivalent to prove that for some p, the norm of this matrix is smaller than epsilon. So if we choose P proportional to the effective resistances of the edges, we can bound this previous quantity thanks to matrix concentration inequalities. For the hypergraph sparsification, we have to prove that this sup is smaller than epsilon. So the quadratic form of H prime is approximated by the quadratic form of H. But differently from the graph case, the quantity above cannot be seen as a matrix norm. So we have to find sampling probabilities such that the expectation of this quantity is smaller than epsilon, and then we have also to concentrate. So that's where the Talagrand chaining is used. So this is a way to bound the expectation of the sup of a Gaussian centered process. So the paper use the Talagrand generic chain to bind the expectation of this sup. This paper of Bansal, Svensson and Luca of 2019 gives a construction of an epsilon spectral sparsifier with epsilon minus 2 and d to the power of 3 log n hyperedges without probability, where d is the maximum cardinality of the hyperedges in the graph. So what did they do is to consider the hypergraph J and then consider the associated graph G to H. This graph is defined such that each hyperedge E of H is a clique in G. And then the weight of the edges in G are given by the sum of the weight of the hyperedge in H for all the hyperedge that contain the pair. They choose the sampling probability to be proportional to the sum of the effective resistance of the edges of the associated graph for every pair of nodes in the hyperedge. And then they study the random quantity, this random quantity. So later, Kapralov, Krautgamer, Tardos and Yoshida show a construction of an epsilon spectral sparsifier with epsilon minus 4 and log at the power of 3 and hyperedges without probability, and later Lee and in the same time Giampolapati, Liu and Sitford show the construction of an epsilon spectral sparsifier with epsilon minus 2 log d log n hyperedges without probability. So they do the same thing of the previous paper, but in a slightly different way. So from the hypergraph H, they consider the associated graph G, defined also such that each hyperedge of H is a clique in G. So then they choose the weight of G in a more careful way, and in particular the weights that satisfy these all inequalities, but I will not get into the details of these. And then they choose the sampling probability to be not proportional to the sum of the effective resistance, but to the maximum of the effective resistance. And then they study this random quantity. So in summary, in the hypergraph sparsification, we define the hypergraph H prime by defining the sampling probability PE. Then we have to study this random quantity, and to do it, we first bound the expectation of it, and then we concentrate. So to bound this expectation, we use the Talagram generic chaining. So in the Talagram generic chaining, one considers a center sub-Gaussian process xt and gives a way to find upper and lower bound to the expectation of the supremum of this stochastic process. So specifically in the hypergraph sparsification case, the set T will be given by all the vector x such that the quadratic form is smaller than 1. And the stochastic process will be the error given by the difference between the two quadratic forms. Okay, so in what follows, I will talk a bit about the Talagram generic chaining. So we have a sub-Gaussian centered process xt. So first the process is centered, so the expectation of each xt is equal to 0. And then we can define a distance in the set T that is given by this quantity. So the distance between S and T is given by the expectation of the difference between xs minus xt at the power of 2. So a sub-Gaussian process xt is such that for every S and T, the tail of this quantity is like a Gaussian process. So there exists C such that this is at most 2 times e at the power of minus c u square over twice the distance between S and T at the power of 2. So, since the process is centered, we can rewrite the expectation of the supremum as the expectation of the supremum minus x of t0 for any t0 in t. So let's see first what happens if we try to estimate this sup using an union bound. So we have that for each u bigger than 0, this probability is at most the probability that each xt minus xt0 is bigger than u summed over all the t in t. So this estimation can be very bad. For example, in the case in which the process is the random variable or the process are identical and the set t is very big, this estimation is very bad. So one can consider a net of t. So first we can fix a subset of t, t1, and we define p1 of t as the nearest point in t1 to t respect to the distance d. And then we can rewrite xt minus x0 as xt minus x of p1 of t and x of p1 of t minus xt0. So for this term, we can do a union bound over all the elements in t1. And for this term, we can choose t1 in a careful way such that this term is small. So the generic chaining generalize this argument. So we consider this like chain of subset of t such that each subset has cardinality at most Cn, where Cn is 2 at the power of 2 at the power of n. Then we can define as before Pn of t as the nearest point in Tn to t respect to the distance d. And we assume that Pn of t is equal to t for n large enough. Then we can rewrite xt minus xt0 as this telescopic sum over n. Okay. Now we can bound the probability that each term of the sum is bigger than this quantity. And since the process is sub-Gaussian, we have that this is bounded by 2 at the power of 2 times e at the power of minus 2 squared, 2 at the power of n. And then we can do a union bound using the cardinalities of the set Tn. So we obtain this bound. I will not get into the details. So this gives us a way to bound the expectation of the supremum that will be at most L times the sup of t over t times the sum over n of 2 at the power of n over 2 times the distance between the value t and the set Tn. So this bound, from this bound we can recover the Dudley entropy bound that gives an upper bound to the expectation of the supremum of the Gaussian process by L times the sum over n of 2 at the power of n over 2 times this quantity, which is the minimum R such that T can be covered with Cn balls of radius R. The Talagram bound is stronger respect to the Dudley bound, and we have first to define the Talagram chaining functional, that is the following quantity. So we have to consider a sequence of partition of the set T such that the sequence is increasing. That means that every set in an plus 1 is contained in a set of an, and the cardinality of each partition an is smaller than Cn, where Cn is this quantity. And if we define an of t as the unique element of the partition an that contains the value t, we can define the Talagram chaining functional at the infimum over all these possible partitions of the sup over t of the sum over n of 2 at the power of n over 2 times the diameter of the set of the partition that contains t. this functional gives itself a bound on the supremum of the Gaussian process, and the interesting part about this bound is that it is also tight, so it gives an upper and lower bound to this quantity. So to bound the supremum of a Gaussian process, one have to define in a smart way the sequence of partition such that this bound then is sufficiently good. So that's all, and thank you for listening.